Okay, so today we're going to talk about polar coordinates. We're just going to do a little introduction in this first presentation. And I think you did a little bit of practice with polar coordinates back when you had pre-calculus. So today, like I said, it's just going to be a little refresher of what we mean by polar functions. So the analogy we're going to use is one way to give directions to tell someone to go 3 blocks east and then 5 blocks south. And that would be sort of equivalent to what we mean in the rectangular or Cartesian coordinate system, like when we say going in the positive or the negative x direction, positive, negative y direction. Another way we could give directions instead to say go a half a mile in that direction. And so I'm kind of, I don't know if you ever heard the term as the crow flies, to give somebody directions, but that's what we're talking about when we say polar. So polar is like the second method of giving directions. Each point is determined by a distance and an angle. So some terms we use in polar coordinates. So the initial ray, we generally draw on what would have been the positive x-axis. Theta is the angle of rotation. So that positive x-axis is also referred to as the polar axis. The origin, where we put the vertex of that angle of rotation, would be what we refer to as the pole. In a polar coordinate pair, we always wrote as r, comma, theta. So r is the distance, how far out you go. Theta is the angle of rotation. One thing that's really different is with rectangular coordinates, each x and y pair has a unique location. For example, -3, 2, that's only one place I can put that on the graph. But with polar, we can have more than one coordinate refer to the same point. And this is because these are all based on what you did with the unit circle and those angles of rotation. There's an infinite number of ways to get to a certain point if you rotate around the unit circle. So for example, if we have the point 2, 30 degrees, that would be equivalent to something in the first quadrant. You could also refer to it as -2, 210. So with polar, if you have a negative r value, 210 in this case refers to we go rotate around 210 degrees, but the negative r value means we go, instead of going out 2 units in that direction, 210, we go the opposite direction. So this could also be -2, 210. Can you think of another example we could use here? If we rotated using a negative angle, that would be coterminal with -150. So that would also be -2, -150. So for this particular problem, all of the polar coordinates at this point are 2, 30 degrees plus a multiple of 360, or -2, -150 plus a multiple of 360. If we were to make a right triangle using polar coordinates, then we can say this. So we have 4 big formulas or identities that we're going to use when we convert between polar and rectangular coordinates. So make a little sketch of this picture on your paper. So this is an angle in standard position. So our polar axis is the positive x-axis. The pole is the origin. So we go at a distance of x units. Theta is our angle of rotation, and so we go up a distance of y units in Cartesian. The hypotenuse is r, and that particular point right there in Cartesian would have been xy. In polar, we're going to refer to it as r, theta. You'll notice tan theta is equal to y over x, just using SOHCAHTOA, opposite over adjacent. And we come up with an expression for x. Well, if you think about cosine theta is adjacent over hypotenuse, then we can say that x is r cosine theta. Likewise, an expression for y would involve sine theta because it's opposite. So y would equal r sine theta. And then last, just using Pythagorean theorem, we could say x squared plus y squared equals r squared. And hopefully these look slightly familiar to you. It's been a while since you've used them, but I think you did use these back in pre-calculus a little bit. Okay, so let's just do a couple of conversions with some coordinates. So let's convert this coordinate to rectangular. So right now we know that this is in polar. The r is square root of 3. Theta is pi over 6. The x coordinate would simply be root 3 times cosine of pi over 6. And of course, if you don't have a calculator, these are all going to be unit circle values. So that just gives us 3/2. Y, remember, is root 3 times sine of pi over 6. That gives us root 3 over 2. And think about if you were to sketch this in polar, pi over 6 would have been in the first quadrant. And since r is positive, the point would have been in the first quadrant, and that corresponds to 3/2 comma root 3 over 2, which in Cartesian would have been in quadrant 1. Make sure your location for your xy coordinate makes sense with where you would have graphed it in polar. Let's do another one, going back to polar. If they're asking you to convert back to polar, then this is obviously x and y. So we need to know r and theta. So let's use the other two formulas that we had on that previous slide. Tan theta, remember, was equal to y over x. This becomes 1 over negative 1. Now think for a second, negative 1, 1, if you were to graph that, what quadrant would that be in Cartesian? That would just be in the second quadrant. So what you want to ask yourself is, what angle on the unit circle in the second quadrant has a tangent value of negative 1? And of course, those are your pi over 4 values, so that would be 3 pi over 4. Now, the reason they're saying 3 pi over 4, of course, is because we have more than one possibility here. Any angle that's coterminal with 3 pi over 4 would get us to that same location. So there's more than one answer. 3 pi over 4 plus 2 pi would get us the same location. R value, of course, is the square root of x squared plus y squared. Pythagorean theorem. That's the square root of 2. The answer is just root 2 comma 3 pi over 4. Again, there's more than one way to write this in polar, but I would just pick the one that seems most obvious. Okay, so if you have your graphing calculator, go ahead and take that out. And let's look at graphing a few of these in our calculator, actual functions in polar mode. So if you recall how to change your calculator, how we changed it to parametric by going to the mode menu, go ahead and do the same thing by changing it to polar, and then try graphing this function. You'll notice when you change the mode, it's now going to say r equals instead of x and y like we had for parametric. And if you think about what this means, r equals 2, this is saying this is the set of all points that are 2 units away from the pole or away from the origin. This is how we graph a circle in polar. And I should say this is how we graph a circle centered at the origin. We'll have some other circles we'll see later on, but this is the most basic. So we have a circle with a radius of 2 units. If we were to convert this back to Cartesian, remember that r squared was equal to x squared plus y squared. So those 4 formulas we had earlier, you're going to want to memorize those. So that means that 4 is equal to x squared plus y squared. And think about it, this is a circle centered at the origin with a radius of 2. Okay, take a look at this one. Theta equals pi over 3. Now, I don't think a calculator will graph this one for you, so let's just kind of talk about what this will look like. They're saying the angle theta needs to be pi over 3. So this would be the set of all points on the line that make an angle of pi over 3 with the positive x-axis. This would just be a line going through the origin. The angle here is pi over 3. So we're talking about all points that are on this line that makes an angle of pi over 3 radians with the positive x-axis. Now, if we were to convert this back to Cartesian, Let's use the formula tan theta equals y over x. I'm going to put in pi over 3 for the theta. And we're just going to crunch the numbers here. So tangent of pi over 3, of course, is square root of 3. So move the x to the other side, and we have the equation y equals square root of 3x. We just have a line through the origin that has a slope of square root of 3. Okay, last thing, let's look at r equals secant theta. This will graph in your calculator, but let's go ahead and convert it first. Remember, secant theta is 1 over cosine theta. I multiply that cosine theta to the other side. We have r cosine theta equals 1. Remember from our formulas earlier, what is r cosine theta equal to? That's x equals 1. So this just gives us the vertical line through x equals 1. If we graph it in our calculator, it gives us a vertical line. One thing that's kind of interesting about this is you'll recall in regular Cartesian mode, your calculator would not graph a vertical line because it's not a function in the traditional sense, but it will do so in polar. So you can see here's a way you can do vertical lines.